Sound is all around us, but some of our most common, everyday noises can reveal amazing secrets about physics. Welcome to our highly tuned and specialized test setup. An anechoic chamber designed to absorb all echoes. This means we'll only hear the direct sound of the impact and no reflections. Our level 2 sound meter captures decibel readings across the full frequency range of human hearing. Our shotgun mic captures clean audio signal. The sound camera pinpoints visually exactly where the sound originates. And the iPhone is used to record slow motion footage so we can see and hear the moment of impact in incredible detail. Sound is the result of oscillations that propagate in a medium, much like waves in a body of water. These waves create high and low density regions that are referred to as compression and rarefaction. The frequency, measured in cycles per second, or hertz, of these waves determine the pitch of the sound. The greater the frequency, the higher the pitch. We have broken down the frequency range of human hearing into 7 different frequency bands to better convey how that frequency band is perceived. You are now seeing the ambient noise level of our anechoic chamber overlaid on this graph. This ambient noise could be contributions from a myriad of sources, like the ground hum of electrical power, HVAC units, and many more. Let's take a look at the sound of an air horn. In the slow motion footage, you'll notice the pitch is dropped and you could see the air escaping the horn. In the full speed footage, you could see how nervous I am. I'm wearing double hearing protection. Let's take a look at the graph. Notice how loud this horn is. Our typical graphs normally only go up to 80 decibels, but for this, we had to scale it up to 120. This loudness can be comparable to operating a jackhammer. Notice the prominence at 800 Hz. For those of you familiar with European football, let's take a look at a Vuvuzela. Let's see what the graph has to say. We see a plateau in the chunk range, which would be its fundamental, that low growl sound. The rest of the spectra is dominated in the warm region, that growl, with it tapering off past the wisp and air regions. Now let's take a look at something we are all familiar with, something that's much quieter, an iPhone vibration. Let's take a look at the spectra. Much quieter than the other two we just viewed. But as you can see, 400 Hz is pretty dramatic in this spectra. It's that warm buzz we are also used to. Now we see all the spectra stacked on top of one another. This gives us a sense of scale of how much quieter the phone vibration is. The decibel scale is logarithmic. So in a general sense, the horns are about 64 times louder to our ears. We look forward to sharing more of our signal archive in the future. Thanks for joining us.